Hi everyone. This video focuses on hypothesis t-tests for two independent samples. I thought I'd start out with something slightly different on this video, and that is I'd dive into a problem. This problem was drawn from a real study, a doctoral study, that was conducted in a local school district. The district sought to increase the ACT preparation of its students, so it purchased a test prep program, a computer program, and encouraged all teachers to regularly use the program with the high school juniors in preparation for the ACT test, which is offered each spring in Kentucky. To determine the impact of the program on students' ACT scores, the district compared ACT scores of all high school juniors during 2012-13, which was the year they used the test prep program, with all high school juniors during the 2011-12 and 2010-11 school year. Rather than doing 2 years as the control comparison, those who did not use the test prep program, I'm just going to focus in this example on ACT scores of juniors during spring 2013, that would be group 1 or sample 1, and ACT scores of juniors during spring 2012, and that would be sample 2. For independence, since the selection of the juniors during spring 2013 is unrelated to the selection of the spring 2012 juniors, the two groups are independent. Okay, so what we're trying to do is we're trying to make an inference about the mean ACT scores, not just of those in the samples, but of all juniors using test prep. That would be our mu1, versus the mean ACT scores of all juniors who do not use test prep or use traditional methods to prepare for ACT. So our hypotheses are: the null hypothesis, the skeptic's hypothesis, is that the means of the two groups are equal. And now we don't really have any indication which method is better, so we'll take a conservative approach, and the alternative is that the mean of the ACT scores, the mean ACT scores of juniors using test prep and those not using test prep are not equal. Group 1, sample 1 are the ACT scores of juniors during spring 2013, and sample 2 are the ACT scores of juniors during spring 2012. Which group is designated group 1 or 2 is irrelevant. That's something you can set in StatCrunch. Okay, so for independent samples, what StatCrunch and every other stat package actually does is it turns the hypotheses into difference statements. If you subtract mu2 from each side of the null hypothesis, you arrive at the hypothesis that mu1 minus mu2 is equal to 0. This statement and the original statement are identical statements. Likewise, for the alternative, if mu1 does not equal mu2, then mu1 minus mu2 does not equal 0. So these are the hypotheses. You can state them in either form, but the computer uses these hypotheses in blue. Okay, so we've got a question about the difference in sample means, whether that difference the difference in population means, whether that difference in population means mu1 minus mu2 equals 0 or not. So what we want to do is we want to use the best estimate of mu1 minus mu2, and that would be the difference in sample means, x1 bar minus x2 bar. Okay, so what we're going to do is we're going to calculate x1 bar, so the mean of sample 1, x2 bar, the mean of sample 2, and we're going to use it as an estimate of mu1 minus mu2. Is that estimate close to 0 or not? All right, here's where a little bit of the theory comes in. Basically, all of this still comes back to sampling distributions and the sampling distribution of the means, since we're doing a hypothesis test for sample means or for population means. Recall for a single sample that if validity conditions are met, sample size of random sample of size n drawn from the population, either the sample size is greater than 30 or the population is known to be normally distributed, standard deviation of the population is unknown, then the sampling distribution, the distribution of sample means, has a mean that's equal to the population mean, has a standard error of the sample standard deviation divided by the square root of n. Again, that's called the standard error. And it follows a t-distribution, which is slightly, it's almost normal. Okay, in this case, what we have is rather than a sampling distribution of a single mean, we've got a sampling distribution of the difference in means. The validity conditions are basically the same. Random samples of size n1 and n2. n1 is the size of sample 1, n2 is the size of sample 2. So random samples drawn from the populations. The random samples are greater than 30, or the populations themselves are normal. So again, there's two populations, one for sample 1, one for sample 2. The standard deviations of the populations are unknown. So very similar conditions to the single sample case. If that's the case, then the sampling distribution of the difference in the sample means has a mean that's equal to the difference in the population mean, has a standard error, which is given by this expression, and also follows a t-distribution. Keep in mind the degrees of freedom of this t-distribution, which essentially is which t-distribution we're using, often is fractional in this case. So you can't use a table even if you wanted to in this case. All right, pictorially, what we've got is we've got a distribution of the difference in sample means. This is a sampling distribution. It's centered, I mean, the mean of the x bar 1s is mu1, the mean of the x bar 2s is mu2, the mean of the difference in the sample means is the mean of the difference in the population means. The spread, or the standard error, standard deviation of this t-distribution is given by this expression. All right, getting back to how do you conduct a hypothesis test for this, let's look back at our hypotheses. If mu1 minus mu2 equals 0 versus mu1 minus mu2 does not equal 0, which was the case in the situation that we had, okay, then the mean of the sampling distribution, which is mu1 minus mu2, is 0. Remember, for any hypothesis test, we assume that the null hypothesis is true. So let's assume that mu1 minus mu2 is 0. So that says this t-distribution of our x1 bar minus x2 bar is centered at 0. Then what we're going to do is we're going to collect the x1 bar and x2 bar and find the difference, and it'll be somewhere. Okay, it might be close to 0, it might not be close to 0. Okay, from that we're going to use the test statistic. Now again, we don't do the test statistic, but this is what StatCrunch will do, is it calculates this test statistic, which is the statistic itself minus the mean, so this will be minus 0, divided by the standard error. That will give us essentially a z-score, if you will. Then use a stats package to determine the likelihood of observing this difference in sample means. In general, for any hypothesis, if the null hypothesis is true, the question is how likely is that observed sample data? All right, let's go back to the problem that we were originally looking at. In this case, I'm going to state the null and alternative hypothesis. This is a presentation of your hypothesis test. The decision rule, we're going to reject the null hypothesis if the p-value, and again the p-value is, going back, is the likelihood of finding that sample data given assuming that the null hypothesis is true. The test statistic is the t-statistic in this case. It's the estimate minus the mean of the estimate, which is 0, over the standard error. All right. What I've done is I've loaded some data into StatCrunch, and here it is. This is our ACT 2013 versus ACT 2012. Let me make sure that what I've got here, I'm looking at group 1 is 2013, group 2 is 2012. So, excuse me, I'm going to go to StatCrunch, conduct a statistics. It's a t-statistic. 2 sample is independent. A paired, again, is dependent. So 2 sample. We have the data, so we'll go to with data. If you're just given the means and standard deviations, it would be with summary, but we have the data. Okay, so value 1, sample 1 is the ACT 2013. Sample 2 is ACT 2012. Just as a technicality, we do not want to pool our variances. Now, our null hypothesis is that the difference in the sample in the population means is 0 versus it's not 0. Compute, and you get your output. Okay, now what I've done is I've printed this output on my PowerPoint file, and here's the results from StatCrunch. Here's the table that we just saw from StatCrunch. Okay, so now let's talk about what this is giving us. The difference is what you're estimating. That is the difference in the population means. The sample difference is the difference in the sample mean. So this is x1 bar minus x2 bar, or essentially the sample ACT, the sample mean of the ACTs in 2013 minus the sample mean of the ACTs in 2012. The standard error is that big expression that we saw a few slides back. Divide the sample difference by the standard error, you get the t statistic. That says what we observed in the difference in the sample means, which is about 9.29, is about 1.26 standard deviations bigger than 0. Again, assuming that the difference is 0, assuming h0 is true. The p-value, which would be the likelihood of observing this, or something even more extreme. Now again, this is a two-sided test, so you would have what StatCrunch is doing is you're actually doubling the p-value and taking the p-value on each side, and so you double it, and that gives you the overall p-values. Again, StatCrunch does this automatically. So if the overall p-value for the two-sided test, the not equal test, is 0.2093, then each side would be half of that, which is about 0.10465. All right, regardless, the p-value is about 0.2. So that says that a sample difference of about 0.92 is fairly common if there really is no difference in the population means, in the mean ACT scores in 2013 and 2012. All right, so the conclusion, since the p-value, which is 0.2093, is greater than 0.05, we do not reject h0. So there's no evidence that the difference in the sample in the mean ACT scores for all students using test prep and all students using traditional methods to prepare for the ACT differs from 0. In other words, there's no evidence that HA is true. So there's no evidence that the test prep program yields improved ACT scores on average than traditional preparation methods. So the district probably should not be investing in this test prep program, at least according to statistics. For the validity of this test, the two samples, which are 2012 high school juniors and 2013 high school juniors, are independent. We'll make the assumption that there's been a random selection of the 99 students in 2012, the 95 students in 2013. Again, I could find that from the StatCrunch data. I could go down and say, how many students did I have? In 2013 I had 95, in 2012 I had 99. Since both N1, which is 99, sample size 1, and sample size 2 of 95 are bigger than 30, we're okay there. Were either of these less than 0, then it would be necessary to construct a histogram of the ACT scores from both samples. Or if one of these fails, you have to construct the histograms. Both sample histograms must suggest you have a normal distribution of ACT scores for all students. The standard deviation of the ACT scores for all students preparing for the ACT via traditional methods and all who are preparing using test prep are unknown. These validity conditions suggest that the sampling distribution of the difference in the sample means. This sampling distribution is a t-distribution. Just a few final comments. You might be thinking to yourself, well, looking at 1 year alone, say 2012 versus 2013, might not be terribly convincing. I agree. For more certainty in the results, you might consider additional years. For example, we compare a couple years of not using test prep with a couple years of using test prep. So 2011 and 12 versus 2012-13. One thing you might also consider is accounting for the possibilities that different classes enter with different skill levels. As we all know as teachers, students come in at different levels, and whole classes come in at different levels. So rather than comparing ACT to ACT, you might compare the quote-unquote growth in scores from plan to ACT. You know, if in both cases they do not use test prep for plan, but one group uses test prep for ACT, the other does not, so the growth from plan to ACT might be greater if you look at the test prep year as opposed to the not test prep year. So it does account for entering skill levels. Another tool, which we're not doing in this class, it's a more advanced tool, it's called analysis of covariance. What it is, it's a tool for considering entering skill levels when you compare some outcome, which would be ACT performance.